Hey there, everyone, and welcome to another episode of HET. So in our last episode, we talked about batteries, specifically lithium-ion batteries, and how they use electrochemical redox reactions to drive an electron from one electrode to another. So the electron here is being at a low potential or voltage. It's being driven over to this cathode here, which has a high potential or a high voltage. And then we can see, these were our reactions here. So at our cathode, we're going at a state of 1.2 volts. Or our anode, we have a state, or electron is going to be at negative 2.9 volts. So again, electrons like to go from low voltages to high voltages. And we have a difference here of 4.1 volts. So if we wanted, we could stack these, batteries in series, which would essentially, if we put another cell on, could get 8.2 volts or double it. Three cells in series, we'd get 12.3 volts, and so on. So today we're going to talk about Ohm's Law and go through some really basic circuits and some stuff with resistors in series and in parallel, and try to dig into, okay, how do we calculate what some of the things are going on in terms of voltage and current as a result of some different configurations. Okay, so Ohm's Law. What does it state? So the basic equation that is part of Ohm's Law is voltage is going to be equal to current times resistance. So we saw that, we can write voltages other ways, being, potential energy per unit of charge, potential energy per unit of charge, or really the change in potential. But anyway, so basically what this is saying is that across a resistor, so if we draw, a basic circuit here, so we're going to have 5 volt power source, then a resistor here, so the voltage difference between this across this resistor, so VR is going to be proportional to the current that is going through it. Okay. So in this circuit, it's really simple. We only have one resistor, so it's just it's going to be simple as, we have 5 volts at the top here, 0 volts down here. So the voltage of the resistor is going to be the same as our battery, which is 5 volts. Let's say we had multiple resistors, so we'll do a really simple series circuit. So again, we'll have our 5 volt power source. But this time we'll have 2 different resistors. And they're going to have values R1 and R2. And for now, we'll keep them the same. They're both going to be 220 ohms. So R1 equals R2. Now, if we wanted to calculate the current that's going through the circuit, we need to determine the resistance of the entire circuit, not just these individual resistors. So for series, the total resistance is going to be equal just to the sum of these two resistors. So R1 plus R2 equals 440 ohms. Then rearranging this equation, V equals IR, we get that, the I total is going to be equal to voltage total over the resistance total. So that's going to be equal to our 5 volts divided by our 440 ohms, which is going to be equal to approximately 11.3 milliamperes. So that's another thing that we should state. So current, it's basically, so it's the change in charge as it relates to time. So, how many units of charge are we moving through in 1 second? So this could be written as, coulombs per second. But more commonly, we're going to refer to this as amperes. As A. So amperes are our units for charge, which is the same thing as coulombs per second. So 11.3 milliamperes is the same thing as 11.3 times 10 negative 3 amperes. This is just a little bit of a nicer form. Okay. So I've actually gone through and taken the liberty of making a model of this circuit. So here, get a little closer up view. We're going to have a 5-volt power supply from this little Arduino thing here. And then I've got 2 leads. So this lead is going to be our 5-volt source. This lead is going to be our ground. And then we have our 2 resistors, which are hooked up in series here. So if we want to take a look at the way that these things are hooked up, get this thing to focus. So essentially everything on these horizontal lines here are all basically on the same wire. So this wire here, that's our 5-volt source, is going to be connected to this node here of this resistor. So that current is going to travel through the resistor to our row 5. It's going to go across to this node of this resistor, go across it, and then end up at our node 10, and then be completed with our ground, just like so. Okay. So then we can take our handy dandy voltmeter over here. And we're going to measure this node and this node, which can be referred to. So this would be our node that refers to this point here. If we measure here, that's going to refer to this node here. And we can see we're getting 14.1 milliamps, which is very, very close to our 11.3 milliamps. So these resistors aren't going to be exactly 220 ohms, and then we got, wires and stuff too. So we have a few variables that are going to make this differ from, our theoretical. But we see that we're very close. Okay, so that being said, what is the voltages across each of these resistors? What is, our V1 here and our V2 over here? So to calculate, our V1, that's going to be equal to our current. And the current going through resistor 1 is going to be the same as resistor 2, right? I mean, so in this circuit, we think of, electrons going, from, this anode to the cathode over here. They all, the only path that they have to go through is through both of these resistors. So it's not like it can, just go around this other resistor. It has to go through all the resistors. So all the resistors are going to have, the same current. But they do have different resistances, right? So, or they are the same in this case. But we can see this later when we go through and start changing the values. So the voltage across the first resistor is going to be proportional to the resistance across that first resistor. So that's going to be equal to our 11.3 times 10 to the negative third amperes times our 440 ohms which is going to be equal no, I'm sorry. So this R1 is just 220 ohms. All right, so that current is going to be equal to 2.5 volts, which makes sense, right? So these are both the same value. So we could do the same thing for V2. Because R1 equals R2, V1 is going to equal V2. So they're both going to be equal to that 2.5 volts. So 2.5 plus 2.5. So V total is going to be equal to V1 plus V2. 2.5 plus 2.5 is equal to 5. And we can verify that with our ohm meter, or with our voltage meter over here. So hooking up our leads, we have, make sure that's on the right setting. All right, hook it up to read voltage. Yep, so we got approximately 2.5 across resistor 1, approximately 2.5 across resistor 2. So now what would happen if we were to remove this 220 ohm resistor and replace him with a 1 kilo ohm resistor? So this is 1,000 ohms. So here we got our 1 ohm resistor here. Take out our multimeter, switch it to the ohm setting. And hooking up our leads, see that we have approximately 1 kilo ohm. Okay, so we're going to put in the one node right here to connect into the other resistor. Put him at the node here to connect him to ground, completing the circuit. All right, now that we got our circuit connected, let's go ahead, draw it up and try to calculate what our theoretical voltage drops and current for the entire circuit will be. Okay, so it's going to be pretty much the exact same thing as our previous circuit. Right, we've got our 5-volt power supply. So this is the positive, this is negative. We still have our 220 ohm resistor right here, so that hasn't changed. But now we have a 1 kilo ohm or 1000 ohm resistor next to it. So our total current throughout the entire thing. So current is always drawn going from, the positive lead of our power supply to the negative side. So right, if we think about what's actually happening, the electrons are going to be going, from, the anode here to the cathode. But for whatever reason, current is drawn as going from the positive to the negative, and that's just the way that, electrical people like to do things, keep us nice and confused. But anyway, getting back to calculating what our total current is. So that's going to be equal to, the total voltage, which is going to be 5 volts. We're not having any separate circuits in here. This is really simple. So go from a potential of 5, we have to go down to 0. And it's going to be divided by our total resistance. So RT is going to be equal to R1 plus R2, which is going to be equal to 1,220 ohms. So it's equal to so our total current is going to be equal to 5 volts over 1,220 ohms. Which gives us a total current value of approximately 4.1 milliamps, or 4.1 times 10 to the negative third amps. Okay. So that's what we expect our, total current to be. What do we expect our voltages to be? So again, total current, has to go through both of these resistors. So the current going through this resistor is going to be equal to this resistor. So we can just use the total current in our calculations. So V1 we expect to be equal to the total current times the resistance at R1. So it's going to be equal to 4.1 times 10 negative third amps. Right, times our 220 ohms. So that is equal to approximately 0.9 volts. Run out of paper. Got that in. So now that we know one of our voltages, we could theoretically calculate the other voltage just by doing the total resistance, minus this V1 here, since, V total is going to be equal to the sum of all the voltage drops, which would be, in this case, just V1 plus V2. So we know what our total voltage is. We know what V1 is. We could use that to calculate our V2 here. But we can just go ahead and calculate V2 same way that we calculated V1. It's another option. So again, that's going to be equal to our total current times the resistance of R2, which is going to be equal to approximately 4.1 volts. So 4.1 times 10 to the 3. .1 volts. All right, so let's go back to our circuit, pull out our multimeter, put him on the voltage setting, and let's see if our readings match what we calculated. So we got going to R1 over here. Yep, about 0.9 volts. R2, approximately 4.1 volts. Yep. So our calculations seem correct. So now what were to happen? So going back to our current or circuit diagrams here. What if we were to change this circuit slightly so that instead of connecting these resistors here in series, what if we try to connect them in parallel? So what do I mean by parallel circuits or parallel resistance circuits? So resistors in parallel. But anyway, we're going to still have, our 5-volt power supply. But then instead of having our resistors in a line, they're going to be parallel to each other so that the current has two different paths that it can take. Right, so before, in this circuit diagram, the current only had one way to go around, so that our I1 was equal to I2, was equal to the current for the total circuit. But here, so we have our total current that's going to be going out from our battery or whatever our power supply is. Is going to be going back into it. Which again is going to still be dependent on our total resistance. So total voltage is still going to be equal to the total current times total resistance. But now we got two different ways for this current to go now. So now we're going to have, this is our R1, it's going to be 220 ohms. R2 is still going to be equal to 1,000 ohms. But so we're going to have current coming in this way. It's our total current. But now we're going to have an I1 that goes through resistor 1, and we're going to have an I2, which is our current going through resistor 2. So if we picture this as a node here, right, the current coming out of this node has to be equal to the current coming into a node. So this is one of Kirchhoff's. So you can draw that out. I'm probably screwing up the spelling, but bear with me. So this is part of Kirchhoff's current law, which states that In for any given node, and a node is just kind of like a fancy term for, a place where wires are going in and wires are coming out. So for any, current going into a node, the current coming out of that node has to be the same. So in this situation, our I total has to be equal to the sum of I1 plus I2. Okay. But how do we know what, our total current is? So for that, we're going to have to kind of go back to this equation, try to figure out, what our, total resistance is. But now we're in parallel instead of series. So we can't just add these anymore. It gets a little bit more complicated. So if we think about what a resistor is, a resistor is really just an impedance to the flow of electricity. So we go back to our diagram here. So 220 ohms is, kind of a lower impedance to electricity, not a whole lot of resistance. 1,000 ohms is obviously more. So all of this resistance is going to kind of add up to each other, since it can only go through this channel here. But now that we have them in parallel, right, we got two different ways that this current can go. So we're essentially going to be reducing the overall resistance, since some of the current can go this way, some of the current can go this way. We've essentially opened up multiple options. So think about like a really packed arena. Someone pulls the fire alarm. Everyone's trying to get out. This would be one door versus now you have two doors, essentially. So people are going to be able to get out more quickly if they have more doors. And then you could say that, the size of the door would be equivalent to, the resistance. So something that's really restrictive, it's going to be an itty-bitty door. Not a lot of people can get out through it. Something that has a lower resistance, so that's just a little 220 ohm resistor here. More people it's a bigger door, more people are going to be able to get out. So what does all of this mean in terms of trying to calculate what the total resistance is? I'm going to save you the trouble of going through some of the math, but basically what we're going to find out is that if you take 1 over the total resistance, it's going to be equal 1 over R1 plus 1 over R2. We know what R1 and R2 is, so 1 over RT is going to be 1 over 220 ohms plus 1 over 1,000 ohms. So we are going to basically take the inverse of this to get our total resistance. Right, so our total is going to be equal to 1 over 1 plus over 220 ohms plus 1 over 1,000 ohms which is equal to 100 ohms. So again, putting the two resistors in series like this effectively reduces the total resistance. So this total resistance is less even than our 220 ohm resistor here. And that's just because we're allowing more pathways for that current to flow. Okay, so how do we set this up on our actual circuit? So again, you know, anything or any of these rows can be considered, you know, an individual wire. So this is just going to be kind of simple as putting all of the nodes on one row. So, okay. So again, so we have our 5 volts in coming through here. So this line or this wire up here corresponds to, you know, this row up here. This row down here at the 5. If you guys can see the 5. It'll focus. Anyway, that corresponds down to this wire down here. So another interesting thing to note is in this parallel circuit, the voltage across both of these resistors is now going to be the same. Why is that, you ask? So voltage is going to be the same across a wire, right? There's no resistance across a theoretical wire. You know, in reality, there's a little bit, but we're just going to say, for the sake of this argument, we're going to say that there's not. So there's going to be no voltage drop across here. So we know that this node is at, you know, 5 volts. This node is going to be at 5 volts. So again, this is our ground or 0 volts here. So we know that this node is at 0 volts. This node is at 0 volts. So 5 minus 0 is 5. 5 minus 0 is 5. So V1 is going to be equal to V2. Man, this marker is terrible. Is going to be equal to the total voltage, which is 5 volts. And we can prove that here using our multimeter. Right, so we got R1, approximately 5 volts, R2, again, approximately 5 volts, 4.9, whatever, close enough. Okay, but what about, you know, our current? So again, going back to this equation here, so now we know what our voltages is going to be across each of these resistors. We know what the resistance is, so we can find the current. So I1, or the current for 1, is going to be equal to, or I'm sorry, we haven't even calculated the total current yet, but we know our total current, so we can do that easily. So that's just going to be equal to our 5 volts over our 180 ohms, which is approximately 27 times 10 to the -3rd amperes. So we know that I1 plus I2 has to be equal to 27 milliamps, or 27 times 10 to the third amperes. Or we could use, you know, this equation again. So we know that I1 is equal to V1, which again is going to be equal to 5 volts over R1, so it's equal to 5 volts over 220 ohms, which is approximately 23 times 10 to the negative third amperes. I2 equals V2 over R2, again 5 volts over 1000 ohms, which is going to be equal to 5 times 10 to the negative third amperes. All right, so our total current, we had a little bit of a rounding error, so this should be a little bit closer to 28 milliamperes. But we see here, so we add our 5 to our 23, you get 28 milliamperes, or 28 times 10 to the negative third amps. So all of that checks out. So that'll conclude this lesson today on Ohm's Law, and then resistors in series and parallel. Thanks for sticking with me through this. I know this is a little bit of a longer of a lesson. If this content helped you in any way, make sure to give this video a thumbs up. Subscribe, really helps the channel and helps me make more videos for you guys like this in the future. Thanks so much. Take care. See you guys in the next one.